Hello adventurer, welcome to Thescratchquest. Today is day 6 of digital logic section in Take from Zero series, and today we'll be learning about Boolean Law. So let's start. So previously we learned about logic gate. Let's have a simple revision of what logic gate is. Logic gate is a simple or small electric signals that takes input 0 and 1 binary number and performs a logical operations and produces a binary output. So it takes the input, it performs a logical operation, and according to the logical operation it gives or produces a binary output. Logic gate is basically an decision makers, and using this logic gate we make decision in computer. It is a building block of computer, and using the logic gate whole computer is built. Now there are billions and trillions of logic gate. Engineers describe the circuit using mathematics. That's where Boolean expression comes to base. For example, we have been using the logical or Boolean expression in our logic gates, or we have learned it. So in OR gate we have all learned that we use the plus sign. We use A or B. This A or B to represent OR gate. This is Boolean expression. Previously we just showed you that to represent the OR gate we use this symbol or this triangle like symbol to represent the OR gate. We also told it is represented by this symbol, and the Boolean expression is A plus B. This is Boolean expression. For AND gate it was A and dot B. For NOT gate it is A complement A complement. So Boolean expression is way to represent the logic gates. And imagine drawing logic gates time and time again, and that's why scientists prefer to use the Boolean expression to represent the logic gates. Now, do you remember doing a question in math? The question goes like, simplify this question. So what we did was we used the algebraic law to make a question or a question small and small and small until it cannot be done using the algebraic laws. Similar to that is Boolean laws. In Boolean expressions there can be a lot of expressions to represent the logic gate. For example, there can be AND gate and OR gate. To represent the mixture of both, we can use A plus B than A dot B. Now that is Boolean expression. What can happen is in Boolean expression we can dim down the Boolean expression. We can, just like how we simplify in math, we can simplify the Boolean expression small and small and small according to Boolean laws. And following the Boolean laws we can simplify into its final form. But why do we even simplify the Boolean expression? Because if we simplify the Boolean expression using the Boolean laws, we can reduce the number of gates, making the circuit faster, making the circuit cheaper, and hence it also reduces the hardware cost. So this is a very important part of building a computer. Scientists use the Boolean laws a lot, but Boolean law is not just like a magic. It doesn't like appear out of nowhere. Boolean laws is just like a set of rules that help to simplify the Boolean expression. It's like a nature of the gate. It is not something that appears out of nowhere. It tells us how gate works, how gate acts. So let's learn the Boolean laws, which are like 10 or 20 of them. I don't really remember, but let's learn the most important Boolean laws. So let's start with identity law. Identity law tells us that the results, the output depends on the unknown number. So for example, in here A can be either 0 or 1. So in this scenario, A plus 0, the result depends on the A. If the A is 1, the answer will come 1. If the A is 0, the answer will come 0. How? As the law, or as we know in the OR gate tells us it doesn't matter if there is even single 1, the answer will come 1 if there is even single 1. So let's say if A was 1, it doesn't matter if it is 0 or 1, all the answer depends on the A. If the A was 0, 0 plus 0 will give us 0. If it was 1, it will give us 1. Similarly, in A dot 1, the answer depends on the A. In AND gate, we tell that it must have both or all the input to be 1 for the output to be 1. But let's say A was 0. It doesn't matter of the result doesn't depend on 1. It depends on the A. If the A was 1, the answer would come 1. If the A was 0, the answer will come 0. This is identity law. Identity of A. The output depends on the identity of A. If the A is 0, the answer will come 0. If the A is 1, answer will come 1. Now let's learn about the second law, which is just opposite of this. That is the null law. Null law tells us the unknown value or the A doesn't matter. So A plus 1, answer will come 1. A dot 0, answer will come 0. It doesn't matter what the value of the A would be. It doesn't matter if A is 0 or a 1. It doesn't matter. The answer will depend on this 1 and 0. Let's see how. So for example, A plus 1 is equal to 1. As we say in an OR gate, even if there is a single 1, the output will be 1. So it doesn't matter the value of A. If the A is 1, 1 plus 1 will give us 1. If the A is 0, 0 plus 1 will also give us 1. So the value of A doesn't really matter. It doesn't change the output. Similarly, in A dot 0, it doesn't matter what's A values. Even if it is 1, as we say in AND gate, the answer would be 0 if there is even a single 0. As there is 0, answer will always be 0. This is the null's law. Remember, this is how gate works. It is not the rule that logic gate must follow, but the rule that represents the nature of the logic gates. Now let's move on to a very simple law, that is idiomatic law. Idiomatic law, I think that's how it is pronounced. Idiomatic law tells us if we use both the similar gate or similar same input, the answer will always be the same input, both in OR gate and in AND gate. Answer will always, the output will always be the input we entered. So for example, let's use a logic gate to see how. So let's say A and A goes through an OR gate. So if let's say A is 1, as they are both A and it is 1 and 1. In OR gate, 1 and 1 will give us 1. If it was 0, 0 and 0 will give us 0. So this value matches the value of A. When it is 1 and 1, it will give us 1, which matches the value of A. So we can say A OR gate A is same as A. Similarly, in AND gate, AND gate, if it was 1 and 1, it was 1, it would give us 1. If it was 0, it would give us 0. So answer depends on answer is same as the output. So A and gate A will give us A. This is a very simple idiomatic law. Now let's go to complement law. This is another simple law. It tells us that A plus A complement will give us 1. and and get a complement will give us 0. Let's understand what. If we all get the input and is opposite of a input, the answer would be 1. And in our second, it tells us if we and get the is input and is opposite input, the answer will always be 0. Let's see how. For example, a plus a complement, it gives us 1. How? So let's say a is 1. A complement is always the opposite of a, so it is 0. 1 plus 0 will give us 1 as the OR gate rule, so it is true. Now let's say a dot a complement, so 0. As we have said, it doesn't matter at all, as we need both the input to be 1 for the output to be 1. But as in here, it breaks the rule. As let's say if it was 1, the 1 would be 0, so it doesn't really matter. 1 but 0 will give us 0. If e was 0, 0 but 1 will give us 0. So the input, it doesn't matter if we are adding the positive which is negative, or sorry, we are and getting is positive which is negative, the answer will always be 0 in here. That is the complement law. Now let's move on to another very simple one, that is commutative law. Commutative law. The commutative law tells us A input and B input is same as B input and A input. So it is telling us the order doesn't matter in OR gate. Similarly, in A and get B and B and get A is same. It is way to tell us the order really doesn't matter in here. Let's see how using an logic gate. For example, A and B, B and A. It goes through an OR gate, both of them. Let's say A is 1 and B is 0. So 1 and 0 will always give us 1, 1. So the order doesn't matter. The same in our AND gate. Now let's go to another little bit confusing but simple one, that is associative law. Associative tell us if there was more than two input. For example, A input, B input and C input. Now it doesn't matter which order we go through, just like in our commutative law where order didn't really matter. If we added A plus B or B plus A. Similarly in here, where there is in associative law where there is more than two input, the order doesn't matter. It doesn't matter if we add A plus B or B plus C or A plus C, it doesn't really matter. The answer will come the same. So the law tells us A plus B, if we do A plus B first or B plus 2 first, it is same. Similarly, A and get B, if we dot A dot B first or A dot B dot C first, it doesn't really matter. Let's prove it using a logic gate. So first of all, A plus A and get B plus C. So we are prioritizing A and get B. So sorry, A or get B. A, B or get, then C is added at here. So or get here. So let's say A is 1, B is 0, C is 1. 1 and 0 in OR gate will give us 1. C will come here. So we go through the OR gate again. So in here 1 and 1 will give us 1. Similarly, let's do B and C first. B and C. C and 0 will give us 1. 1 and 1 will give us 1. I hope you understand the associative law too. Now let's do the distributive law. The distributive law tells us if there is A AND gate and prioritizing B plus C in a bracket, it is same as saying A and get B and OR get A and get C. So what we are doing is here we are distributing it. Distribute law tells us we can distribute the A dot A and get with B and C using the OR gate. So what is happening is here we are distributing A and get with B, give us A and get B, and the OR gate in here will give us the OR gate in here, and A and get C give us A and get C in here. So we are distributing we are distributing the A in both of them using the OR gate in middle. Let's see with an logic gate. A dot B plus C is same as A dot B plus A dot C. So let's do this first. A B C and get. So last we do and get. Let's assume it is 1 0 1, just like what. So first of all 0 and 1 in OR gate will give us 1. A is 1, so 1. 1 and 1 in AND gate will give us 1. Now let's do the another one, which is A dot A dot B plus A dot C. That is it, I think. Okay, now let's draw this the logic gate, which is A B A C in AND gate and OR gate. So let's say 1 0 1 1. 1 and 0 will give us 0, 1 and 1 will give us 1, 1 and 0 and 1 will give us 1. So this is proved, hence proved. Now let's do the absorption law. Absorption law tells us that A and get A dot B is A, and A and get A plus A or get B is A. Let's understand how. Let's do the first one, that is A and get A dot B. Let's minimize it using Boolean expression, and let's understand how this is A. Let's say A is 1 plus 1. It is let's say B can be 0. If B was 0, 1 and 0 0 1 plus 0 1. If B was, let's say, 1, if B was 1 1 plus 1 1 1 1. See here the pattern. It doesn't matter what the value of B is in here. B is redundant. It doesn't matter what B is. The answer is always the value of A. Did you see? Let's do this again. The value all depends on the output, all depends on the A. If the A was 0, for example, 0 plus 0 dot, let's say B was 1. It doesn't matter, as in AND gate the answer would always be 0 if there was even single 0. The answer would be 0, which is same as the value of the A. Let's say all the value, if A and B was both 1 plus 1 dot 1. 1 and 1 dot 1 will give us 1, and 1 OR get 1 will give us 1, which is again the value of A. So it doesn't matter what the value of B is. It is always the value we get is always the value of A. So in here this law tells us that we need to find the redundant value which doesn't really matter, which doesn't really impact the output. We need to find that. This is one of the like law that is really confusing. We need the basic understanding. Similarly, let's do the another one, which is a dot a plus b is equal to a. Similar to that, the value of b doesn't really matter. The value of a determines the value of b. That's why it is a. Even if b was 0 1, it doesn't impact the output. That's why we put a. Similar to that, let's see how. So a, I say a was 1 plus, and b was 0. 1 dot 1 plus 0 1 1 dot 1 1. If let's say a is 0 and b is 1, 0 dot 0 plus 1, 0 dot 1 0. See the pattern? The answer always is same as the a. That's why we don't use the b, as b doesn't matter if b is 0 1. The answer would always be the value of a. This is observation law. Observation law observes. This might be confusion at first, but as we go and learn, this becomes really simple. Really simple. Now let's do the another one. That is De Morgan's law. It tells us a plus b whole complement is same as a single complement and get b single complement. Similarly, a and get whole complement is same as a complement or get b single complement. You may ask how. Let's see using the OR gate, using the logic gate. So for example, a and b, to present the OR gate we use this, and to represent an whole complement we use NOT gate in this top. So here, let's say a was 1 and b was 0. 1 and 0 would give us 1, and the 1 would be converted into 0. Now it converts the output in a plus b whole complement. Let's say this was a b and, which is the answer, which is a and get dot b and get. When we see a single as single complement, we put the NOT gate before going to the logic gate. So in here, let's say a was 1, just like here, and b was 0. So 1 becomes 0, 0 becomes 1. 0 and 1, it doesn't really matter. In AND gate, if there is even single 0, the answer would be 0. If it was both of them was 1, it would be 0. If both of them was 0, for example, it would give us 1, and in here also we would get it 1. So yeah, I hope you understand this De Morgan's law. Let's do another simple one, that is a dot a and get b is similar to a single and b single OR get. Let's do the first one, that is a b and get will give us, let's say, 1 and 0. 1 and 0 will give us 0, 0 will give us 1. Similarly, a complement 1 and 0, 1 will 0, 0 is 1, and OR get, which will give us 0 and 1 will give us 1, as even if there is even single 1, it will give us 1. I hope you understand these Boolean laws. The video has become really long. I try to explain each and all the law as simple as I can. So I hope to meet you I will meet you in next video of digital logic. It's been a really long time since I posted. So yeah, bye bye.